we'll move on. So the next thing we'll be doing is we're going to be looking at a series called the harmonic series. All right, harmonic series. Okay. All right, so let's start off with a definition. So I'll shorten definition to just DEF, which you guys have seen me do already. Okay, so DEF stands for definition. All right, so here we go. So we're going to define the harmonic series right now. So a very famous and useful series is the so-called harmonic series. Okay, so that's what we are defining in this definition, so I'll underline it, which is defined as is this infinite series. So it's going to be the sum from n equals 1 to infinity, and the expression that we're summing over is just 1 over n. Okay, so let me just write out a few terms of this guy. That's just going to be 1 plus a half plus a third plus a quarter, and so on forever, plus dot, dot, dot. All right. So that's nothing too crazy. So we're going to be interested in investigating whether this series converges or not. Okay. So does it converge? Question mark. Okay. And we're going to develop tools later to answer that question. All right. So we will develop tools later in class to answer that question. Okay. So does anyone want to take a guess maybe as to if this thing converges or diverges?
Does it converge?
Maybe. We'll see. So you say it converges. So Aiden, I think, raised his hand. What do you think?
I am going to guess that if the denominator continues to get smaller and smaller and smaller, that it will converge to 0.
Uh-huh. Well,
I don't know.
I see what you're saying is that the denominator needs to get really big so that we're summing small numbers. But
Like bigger and bigger and bigger, I'm sorry.
Right, no, right. That's completely correct. But how could it converge to 0 if already we're adding 1 into the sum? You see what I mean?
Okay, maybe I need to understand how this works a little bit better.
Yeah. So maybe the 1 over n is getting close to 0 fast enough so that we're summing up really small numbers at the end. So it does converge. So we're going to see later. So far, someone said converge. Someone said, yeah, so both.
I say diverge.
And Tori says diverge.
Because I watched Professor Leonard earlier on YouTube.
Okay. I like that guy. He's cool. Okay. So spoiler alert. But I don't know. Maybe he was wrong. Let's see.
Sorry.
Anyways, so we're going to see later, and we'll prove that it, in fact, converges or diverges. All right. So that's a very famous series. It comes up in mathematics all the time. I've seen it a lot in grad school. All right. So that's harmonic series. Now let's look at something called telescoping series. Okay. Okay, so before I define what a telescoping series is, I'm actually just going to give an example of one, okay, because that will motivate the definition a little better. All right, so let's look at this series. Let's look at this guy. Sum from n equals 1 to infinity of 1 over n times n plus 1, okay? So we actually showed last class on Monday, that this thing converged, okay? So we showed last time that, well, we actually did even better. We showed last time that the sequence of partial sums, Sk, had the explicit formula k over k plus 1. Okay, so that was last class. Hope that seems a little familiar. So we showed that the sequence of partial sums had this form, which implies that the sum converges to 1, because the sequence converges to 1, okay? Which implies the sum converges to 1. All right, so I hope this implication is clear. It's literally by definition, because this sequence has limit 1, okay? All right, so actually let's consider a slightly different technique to get at the sequence of partial sums, all right? So let's try something different. Let us consider a different technique. All right, so, oops, that's not how you spell technique. Okay, so let's actually apply partial fraction decomposition to the sequence that we're summing over. Okay, so let's decompose that 1 over n times n plus 1 guy. All right, so let's do that. I mean, why not? 1 over n times n plus 1. So this is the case 1 non-repeating linear factors. Okay, so this is going to take the form a over n plus b over n plus 1. Okay, so that should look familiar. All right, so we just have to multiply both sides by n times n minus 1. This gives us a is equal to 1 is equal to a times n plus 1 plus b times n. And I think it's best to use strategic substitution, so we can just let n equals 0, which will imply that a is 1. And let's let n be minus 1, which will imply that b is negative 1. All right, so that's quick. It's a very easy partial fraction decomp. All right, so thus our sequence formula, so thus our guy 1 over n times n plus 1, it takes the form, well, a is 1, so I'm going to put that in there. That's 1 over n. B is negative 1 minus 1 over n plus 1. All right, so that's just good old partial fractions. So consequently, our sum takes the form. Our sum can be also rewritten as, I'm just going to plug in our partial fraction formula in for the original guy. So it looks like 1 over n minus 1 over n plus 1. All right. So it's the same exact sum. We just did partial fractions on the sequence formula. All right. Good. So now let's just look at the partial sums of this guy. So we're just looking at a different way to view the partial sums. So let's look at partial sums of that series. All right. All right. So let's do that. So S1 is just going to be the first term in the sum. That's what it always is. So that's going to be 1 minus half. Okay. Okay, cool. S2, it's going to be that 1 minus half. So I'm going to introduce parentheses just to make things nice and neat. Plus, now the second guy will be 1/2 minus third. Okay, but we see that these 1/2s, they cancel. We have minus 1/2 plus 1/2. That goes away. They turn to be 0, and then we just have 1 minus a third. Okay, so let me just highlight what's going on. This minus half and that half cancel. All right, and now let's look at S3, third partial sum. A 1 minus half plus half minus third, and then plus 1/3 minus fourth. Okay. All right. And the same thing happens, except we get more cancellations. The 1/2s cancel and also the 1/3s cancel. Okay. So we're just left with 1 minus 1/4. Okay, cool. So from which it is clear that we can actually get an explicit formula again for the sequence of partial sums, from which it is clear that Sk, our sequence of partial sums, has what explicit formula? So does someone want to try and get the formula?
1 minus 1 over n.
Close. So the 1 minus was right, but look at the subscript here and look at the
1 minus 1 over n plus 1. Sorry, yeah.
yes, exactly. So our sequence of partial sums has the explicit formula 1 minus 1 over k plus 1. Great. Now we just take limits as k goes into infinity, as k goes to infinity. So this implies that the lim of sk as k goes to infinity, well, that's just going to be 1. All right, because this summand here goes to 0. This guy goes to 0, okay? That goes to 0. All righty, so that's cool. So we ended up with the same exact answer that we obtained last class. So that's cool. Anyway, so this kind of motivates the definition of a telescoping series, all right? So the middle terms in each partial sum cancel, which is reminiscent of a telescope shortening, okay? So the telescope shortening, you know, you can like stretch it out and it retracts and all that stuff, the telescope shortening. So this motivates the following definition. This motivates the following definition. All right, so here is the definition of telescoping series. So a telescoping series, okay, and I'll underline that because that's the word we're defining. Telescoping series is a series in which most of the terms cancel in each partial sum, leaving only some of the first terms, leaving only some, S-O-M-E, some of the first terms and last terms, okay? Alrighty, so we saw this occur in the previous examples. Those middle terms canceled, and we were just left with terms in the beginning and the end. All right, so that was an example of a telescoping series, but we were only able to verify that it was a telescoping series after we performed partial fraction decomposition. It wasn't apparent in its original form. All right, so let's look at another example. Okay. Let's look at, so this one's kind of cool. Let's look at the sum from n equals 1 to infinity and the sequence that will sum over. This will be cosine of 1 over n minus cosine of 1 over n plus 1. All right. 1 over n plus 1. All right, so that's our sequence that we're summing over. And just like before, let's look at the first few partial sums and see if some sort of pattern emerges. Maybe you see it already, because it looks very similar to the previous example. Anyways, S1, that's always just the first summand. That's me cosine of 1 minus cosine of a half. And S2, this will be cosine of 1 minus cosine of half, plus cosine of a half minus cosine of a third. Okay? And in the second partial sum, S2, the cosines of half, those cancel, okay? So we're getting the same kind of deal. So this is, so this just reduces down to cosine of 1 minus cosine of a third. So we should be able to pick out the pattern. So in general, our SK is what? So does someone want to give me the explicit formula?
I can.
Oh, yeah, Carolyn, please.
SK equals the cosine of 1 over k minus the, I'm sorry. Yes, the cosine of 1 minus the cosine of 1 over k plus 1.
Perfect. Exactly. Thank you. So the SKs, as she said, it's going to be cosine of 1 minus cosine of 1 over k plus 1. Exactly. So it looks very similar to the previous example. All right. And now it's really easy to see what this series converges to. We just have to take the limit as k goes to infinity of sk. All right. So we're actually going to use our theorem from last class that continuous functions preserve sequences. So let's use that. So we note that the input of cosine 1 over k plus 1, that converges to 0. Okay. And cosine x is continuous at 0. Okay. So now we're going to apply that theorem from last class. So the assumptions of the theorem have been satisfied, so we can apply the theorem. Thus, lim of sk, that's going to be lim of cosine of 1 minus cosine of 1 over k plus 1. And this will just be cosine of 1 minus cosine of 0. Okay. So I hope that's clear. I just applied that theorem from last class to that second summand in the parentheses, okay? And this is cosine of 1, and cosine of 0 is 1. So the answer is cosine of 1 minus 1. Okay.
I have a question. So are all telescoping series have a minus sign in their sums? Because that's the way they cancel out.
Yeah, so there definitely needs to be some sort of alternating of pluses and minuses. Yeah,
Okay.
definitely. All right, very good. So does anyone else have any questions about this? This was final answer. We don't have a nice value for cosine of 1. It's not one of our nice trig values, so we just leave it like that. Okay. All right, so I will move on then, if that's okay. All right, so we finished with telescoping series and harmonic series. Now we're going to go on to our various tests of divergence and convergence of an infinite series, okay? So this is really the heart of the second half of the course, okay? All right. So first test is called the divergence test. Divergence test, okay? All right, so just a quick description of this test. It's a quick test. quick test to see if a given series diverges, as the name suggests, right? So it's a quick test to see if a given series diverges. It does not tell us about the convergence of a series. It just tells us if the series diverges. All right, so here's the theorem. So all of the tests for convergence and divergence, they're all theorems, okay? So it's a theorem, and it's called divergence test, as you could guess. Divergence test. All right, so what is the divergence test? Okay, so let's let this n equals the sum from n equals 1 to infinity of an be an infinite series. Infinite series. Okay, and the statement is simply this: if lim as n goes to infinity of an, so just the sequence that we're summing over, just this an guy, if the lim as n goes to infinity of an does not equal 0, or if lim an diverges, hold on, lim as n goes to infinity, or if the limit diverges, then the series, the infinite series, this will tell us that the infinite series diverges, okay? So very quick test for divergence. So if the limit is 0, or if it diverges, then the series diverges. Yes, exactly. All right, so I hope this statement is clear, and it's very important to note that if the limit is 0, so this is very important, if the limit of an does equal 0, the test is inconclusive. It tells us nothing. It does not mean that the series converges, okay? The test is inconclusive, which is to say that it tells us no information, okay? So this is a common mistake that I've seen before. A student will say, oh, well, the limit of an is 0, so the series converges. That's not true. Okay, so there are series whose sequence terms go to 0, but their series diverge, which we'll see. All right, so before we prove this, and the proof is quite quick and elegant, let's just do a few applications. All right, applications of the theorem. All right, so okay, so we'll do applications, and then we'll do the proof. All right, so applications. Applications of divergence test. Okay, example. So let's look at the sum from n equals 1 to infinity of n over 3n minus 1. So all we have to do is just look at the limit of the sequence that we're summing over. So we just need to consider or examine the lim as n goes to infinity of this function here, this n over 3n minus 1. Okay. So this should be a fairly easy limit. You can just use L'Hopital's if you'd like, and you will just get 1/3. So I hope that's okay. And 1/3 is of course not equal to 0. Thus our series diverges. That's it. All right, because that's what the divergence test told us. If the limit of the sequence is not 0, then we know our series diverges. And that's all there is to it. So let's look at some more. And of course, always stop me if you have questions. So example, let's look at the sum of 1 over n cubed. Let's look at 1 over n to the 3rd power. All right, so all we have to do is just look at the limit of 1 over n cubed. So we look at 1 over n cubed. This is 0, actually. Okay, that's 0. And if you look up, the divergence tells us nothing. So the divergence test tells us nothing if the limit is 0. So the divergence test is inconclusive. So we don't know anything about this series. Or the divergence test tells us nothing about this series. All right. So the divergence test is inconclusive, okay? So please don't tell me that this series converges because the limit is 0. All right, hope everyone's still with me. So let's look at another. Let's look at the sum n equals 1 to infinity of cosine of 1 over n cubed. No, 1 over n squared. 1 over n squared. Cosine of 1 over n squared. Alrighty, so all we need to do, as the divergence test states, we just need to look at the limit of the sequence that we're summing over. So we just need to look at the limit of cosine of 1 over n squared, okay? Very good, so this is now an instance where we'll use that theorem that continuous functions preserve sequences. So that just means we can interchange the limit with the cosine, okay? So that's equal to cosine of the limit. All right, so this is just that theorem from last class of 1 over n squared. All right, so that's by continuity of cosine. All right, and this is just now cosine of 0, which is 1, which is not 0. Great. So the limit is non-zero, so the series diverges. Very cool. All right, so I think that's it for examples. Yeah. Yes. Okay, so now let me just consider the proof of this. Okay. So this is a cool proof. So let's look at proof of divergence test. So we're actually going to prove the contrapositive. All right, so let me just write that. We will prove the contrapositive. Okay, so the contrapositive is an equivalent statement. If you prove the contrapositive, that works. You can always do that when you're proving a theorem. Okay, so what is the contrapositive? That is, we will prove. So here is the contrapositive. If the sequence converges, if n equals 1 to infinity an converges, then lim of the ans equals 0. Okay, so that is the contrapositive of the divergence test. Okay. So I hope that's Okay. All right, so that's what we'll set out to prove. We're going to assume AN converges. We just want to show that lim of AN equals 0. All right, so before the proof, we just need a simple fact that we're going to call upon in the proof. Simple fact. And that is to say that the kth partial sum minus the k minus 1th partial sum. I'm going to use that. So the kth partial sum minus the k minus 1th partial sum, that's actually just equal, well, let's just work it out quickly. So that's equal to the sum from n equals 1 to k of an minus the sum from n equals 1 to k minus 1 of an. Right? And then you'll see that if you actually write all of this out without the sigma notation, the only term that's going to survive here will just be the lonely AK. All right, so I hope, so you can convince yourself of that pretty easily. All right, so we're going to use this simple fact in the proof. Okay, so remember, we're assuming that the sum converges as per the contrapositive states. So since AN converges, so we have to use that assumption, we have that S, which equals lim of k goes to infinity of sk, that converges as a sequence. That converges as a sequence. And that's should be easy to see. That just follows from the definition of an infinite series converging. We know that the limit of the partial sums converge. All right. So with that in mind, let's consider. All right, we're gonna look at lim of AK, A sub k. And remember, we want that this limit to be 0. We want this to be 0. Okay, very cool. So lim of AK, that's the same as lim as k goes to infinity. And now let's use our simple fact. AK can be rewritten as sk minus sk minus 1. Okay, and that's by simple fact. Okay, so I have rewritten our a sub k as that. Very good. And now, according to our algebraic limit laws, I can distribute the limit to both terms here. So that's going to be lim of sk minus lim of sk minus 1. So that's just by properties of limits. So that's those algebraic limit laws from last class. And these are both exactly the same sequence. The only difference is the subscript is different by 1, but once k goes to infinity, the difference of subscript does not matter. So this is just s minus s, which is 0. Right, because if I let the quantity k minus 1 tend to infinity, it's the same as letting the quantity k tend to infinity. It's just a change of variable. It doesn't change anything. All right, so both of these limits are s. So that's why we have s minus s, and that's 0. And that's it. We have proven that the lim of the AK is 0. So any questions about that? That's a pretty slick proof.
Did you say if being, I guess, the series divergent and a sum, I guess what I'm asking is, can there be a sum to an infinite series that diverges? It seems like that's a condition you expressed in one of these, but it also seems like you should be able to do that.
So you're asking if there are infinite series that diverge?
Does a divergent series necessarily not have a sum? can you sum a divergent series?
Oh, right. So classically, no, you can't, not in our setup here when you take the limit of the partial sums, but there are alternative summing things called, there's something called a Cesaro sum, and that's an alternative definition to taking sums, and you can sum up divergent series and you can assign some sort of meaningful value. Yeah. So if you
Okay. But for our purposes, divergent means it doesn't sum.
exactly.
All right, because when we read that harmonic, then I'll be interested to go back to the harmonic series because it looks like it should add up to something.
Exactly. It does. Yeah, you would think, because you're adding very small terms towards the end.
Like 1 plus 0.9 repeating.
Right. Yeah. So
You
we're going
know,
to do that.
or something like that.
So yeah, so this is something called Cesaro sum, and this allows you to assign some meaningful values to classically divergent series. So that's something extra. Yeah. So if you want to look into that, that's some cool stuff. This is Cesaro sum. All right. Very cool. Very cool. All right. So if no one has any questions, I will go to the next test. And that's going to be called the integral test. The integral test. Okay, and all of these tests are theorems. So here we go, theorem. Okay, so the first assumption is that we need all of the sequence terms to be positive. All right, so we're going to suppose sum an. So I'm going to omit the n equals 1 to infinity for now because it just gets a little cumbersome to write. So suppose an is a series with positive terms. So such that each term a sub n is greater than 0. Okay, for all n in the naturals. Okay, so what does this upside down a mean? That just means for all. So that means for all. So that's just shorthand for all natural numbers. N. Okay. Next, let f of x be a function such that. Okay, so we're going to have 3 conditions on this function f. 1 is that f is continuous. 2, f is decreasing, which is really just to say geometrically is that that its graph is going to look something like this. All right, it's going to go down as you travel out on the x-axis. Okay, so it looks like that. There is a more rigorous definition for decreasing, but we don't need it. And then the third condition will just be that our function agrees with the sequence terms on the natural numbers. So f of n is equal to a sub n for n bigger than or equal to some capital N. Usually our capital N is going to be 1. Usually our capital N will be 1, which is just to say that our function agrees with the sequence terms for natural numbers. That's all it is. All right, so these were all the assumptions. So what's the conclusion of the theorem? Then, if the following hold, then the infinite series an and the improper integral of f of x dx. So the lower limit of integration is this capital N, but it will usually just be 1. I think all of our examples is going to be 1, so don't worry too much about that. So then this and that have the same behavior. So that is to say, they either both converge or they both diverge. All right, so either both converge.
If they converge, will they converge to the same value?
Great question. And the answer is no. No. And I was going to write that next, so thank you. So, but not necessarily I don't know how to spell this word, but not necessarily to the same value. Okay, so that's very important. Okay, so there do exist sums, infinite sums and improper integrals that both converge, but the values are not the same. All right, so there are examples that show this. It's not necessarily to the same value. You can search on YouTube for that. I think I've seen videos of that. Okay, so that's the statement. So basically this theorem tells us we can take an improper integral and examine the convergence or divergence of that to determine if our infinite series converges. And we know how to do improper integrals, so that's good. All right, so the proof is omitted. So this is actually not a very nice proof, so we're not going to do it. So proof omitted, all right. But there are proofs online of this if you're interested. So let's just jump straight to applications of the integral test. All right, so let's look at applications. Applications of integral test. All right, very cool. So first one, let's look at the sum from n equals 1 to infinity of, I think we've looked at this sum before, 1 over n cubed. So we tried to use the divergence test on this guy, and we saw that the divergence test was inconclusive. Told us nothing. All right, so let's see if, so let's give the integral test a shot. Let's see if it will help us out here. Anyways, so for the integral test, we need a function f that satisfies those three conditions. That is not hard. All you usually need to do is just consider the sequence formula and put an x there. So basically, just let f of x be 1 over x cubed. All right, that's usually what you're going to do. All right, then f is decreasing, continuous, with f of n, so f restricted to the natural numbers, agrees exactly with our sequence. F n equals, right, for all n in the naturals. Very good. So let me just quickly point out, it's decreasing and continuous on the interval 1 to infinity. Okay. Very good. So thus, we can look at the improper integral from 1 to infinity of 1 over x cubed dx to determine convergence, to determine convergence / divergence of our given series, which was 1 over n cubed. All right. So it suffices to look at this improper integral, excuse me. But what's cool is that on homework 3, we actually considered this guy. So, but on homework 3, we showed, or you guys showed, that the improper integral of 1 over x cubed equals, I think it's a half, equals a half, which is convergent. Okay, so I hope you guys recall that. Yeah, so we're done. So since the improper integral converges, we know that our initial sum converges as well. So by integral test, sum 1 over n cubed also converges. Very cool. So that's this, so converges. So that's the link that this theorem tells us. the behavior is the same. Okay, but not necessarily 2 1/2, but not, I have to spell that, I don't know how to spell that, but not necessarily 2 1/2. All right, so very important note. Okay. All right, so we're almost done, actually. All right, so any questions about using this theorem? We're going to do some more examples. Okay, so now we're going to go to the harmonic series. All right, we are now ready. We're now ready to show that the harmonic series, well, I'm going to spoil it, diverges, crazily enough, diverges. All right, so the harmonic series, as I said earlier, is it's nothing other than sum from n equals 1 to infinity of 1 over n. Okay. So the function we're going to consider for the integral test, it's pretty obvious. You just replace n with x most of the time. So let f of x be 1 over x. All right, then f satisfies the assumptions of the integral test. Okay, so when you write this up, like when you're doing your own examples on homework for the integral test, I would appreciate just a small line about this, that the assumptions are satisfied for the various tests. All right, very cool. So that means we can just look at the improper integral from 1 to infinity of 1 over x dx. All right, and we're all pros at improper integrals now, so I'm just going to do this really quick. This is a limit. By definition, it's a limit as t goes to infinity from 1 to t. That's by definition. Good, and now we can take the antiderivative. Next step. Antiderivative of 1 over x is natural log of x. Evaluated from 1 to t, plug in, okay, lim. Okay, plug in the upper limit of integration and plug in lower limit, ln of 1. Very good, and natural log does shoot off to infinity as t goes to infinity. So this is infinity, so it diverges. Okay, so this is something that we've considered before. I think we've done this improper integral before. Thus, our original series converges. Thus, the harmonic series diverges by the integral test. All right. Okay, so the behavior, let me just restate this, is exactly the same. That's what the integral test tells us. So diverges, diverges. Okay, and we have a nice correspondence here via the integral test. Okay. What else? Okay, cool. So that's it for integral test. We're actually going to go back to it in a proof really shortly. So any questions before we do the final topic of tonight? All right, so I'll move on. So next thing, definition. Okay, so this is very, very nice. For any p in the real numbers, so that's what that notation means. For any p in the real numbers, the series sum from n equals 1 to infinity of 1 over n to the pth power, okay, that's what we're defining, is called a p series. Okay. This is a very special type of series. Lots of applications in upper level math. So the theorem that goes along with this definition, so we have a nice quick criterion for when a p-series converges, okay? So this is called the p-test. Yeah, it's called the p-test. That's the name of this theorem. All right, and it states this, a p-series diverges. So if that exponent p, if p is less than or equal to 1, okay, and converges if p is greater than 1. Okay. So diverges if p is less than or equal to 1, and converges if p is greater than 1. So just note that the case of p equaling 1 is precisely the harmonic series, okay? And we have already shown divergence of that. So our proof, we're not going to consider p being 1, since we already proved that. All right, so let's prove this. So this proof is a really nice application of the integral test. So that's why I want to consider it. All right, proof. Well, it's actually an application of a few tests that we did before. So anyways, so let's just look at, let's just look at case 1, which will be when p is less than or equal to 0. Okay, so let's look at that first. So first of all, if p is strictly less than 0, then the sequence 1 over n to the p, that goes to infinity. So it diverges. Okay, because if the exponent of n is negative and it's in the bottom, you bring it up and it turns positive. Okay, so we have n to a positive power, and that's going to go to infinity. Okay, so it diverges. So by the divergence test, that was the first test we considered. By the divergence test, the series diverges. Okay, so I hope that's clear, because the sequence itself goes to infinity, it diverges, so the divergence test tells us that the series diverges. Okay, so we just took care of p being less than 0. Let's look at if p is precisely equal to 0. Well, then what does the sequence look like? We have 1 over n to the first power, 1 over n to the 0 power, which is 1. And as a sequence, that converges to 1, right? And that's not 0. So by the divergence test again, the series diverges. All right, so we're just using the divergence test here. Since both of those sequences diverge, or they don't, or they converge to something that's not 0, divergence test tells us that the series diverges. All right, so we took care of p being less than or equal to 0. All right, so let's look at case 2. Case 2. So this is p being strictly greater than 0, but p not being 1. because we already took care of p being 1. That's the harmonic series. That's why I'm not considering p equals 1. All right, anyways, so now we're going to use the integral test, okay? So if p is greater than 0, the function f of x equals 1 over x to the pth power. That satisfies the assumptions of the integral test, okay? Satisfies the assumptions of the integral test, okay? So we investigate convergence of the improper integral, and that will tell us the behavior of our series. So we investigate convergence of now the improper integral from 1 to infinity of 1 over x to the p. All right, so we just need to compute this guy. Anyways, by definition, this improper integral is a limit as t goes to infinity of 1 to t of x to the minus p. So I'm going to bring that x to the pth power up top. Comes out as a negative exponent. So I hope that's okay. Cool. Next, I'll take the antiderivative. So I'm going to use the power rule. So this will be lim as t goes to infinity. Lim as t goes to infinity. So if I use the power rule, well, that's just you add 1 to the power and divide by that new power. That's all that is. Evaluated from 1 to t. Very cool. So this comes out to lim as t goes to infinity. This comes, so I can pull out a 1 over 1 minus p. So that does not depend on the limiting variable t. So I'm just going to pull it out. And this is t to the 1 minus p minus 1. Okay. So that's that. All right, so here we go. So now we have some sub cases. So now, if p is strictly greater than 1, this term here, this t to the 1 minus p, that limits to 0. Okay. And if p is between 0 and 1, that term goes to infinity. All right, so we just have convergence if p is greater than 1. Okay, because then this term here goes to 0, and the improper integral comes out to a finite value. All right, thus, we only have convergence if p is greater than 1. So we're done. So our result follows now by the integral test. Our result about the infinite series, 1 over n to the p follows by the integral test. All right, and we're finished with the proof. All right, so any questions? So I think the most confusing part of this proof is this right here, these two statements. If p is greater than 1, then t to the 1 minus p goes to 0, and also the second one. So let me just maybe explain that. So if p is greater than 1, then 1 minus p is a negative value. So that the exponent's negative, so you bring it downstairs, and then you have 1 over infinity, and that goes to 0. Right? And if p is between 0 and 1, then 1 minus p is positive. So this exponent stays up in the numerator, and t goes to infinity. So that's that explanation. So any questions? Alrighty. All right, so we're going to end with just very quick applications of the p-test. So, applications of p-test. Right. Okay, so example. So it's really not bad. So n equals 1 to infinity. Let's look at 1 over n to the 4th power. Okay, so in this case, what is p? In this case, well, p is 4. So it's precisely the exponent of the n. Well, 4 is greater than 1. Thus, the series converges. All right, so that's exactly what the p-test tells us. If that exponent on n is strictly greater than 1, the series converges. Okay. So, not bad. Let's look at another. How about this one? How about 1 over n to the 2/3? Okay, so what's p here? And does it converge or diverge? So someone want to shout it out?
P is 2/3, and since it's less than 1, it diverges.
Exactly. So p is 2/3, which is less than 1. Thus, series diverges. Excellent. All right, so p-test is really useful. And final example. How about this one? How about sum from n equals 1 to infinity of 1 over n to the pi-th power? How about this one? So
I guess I'll do it again.
Yeah.
P equals pi, and pi is greater than 1 because it's 3.14 or whatever. And that means it converges.
Excellent. Yeah, p is pi, 3.14, blah, blah, blah. That's definitely greater than 1. So the series converges. Excellent. So p series is really quick way to see if these special series 1 over n to the pth power converges. And let me just point out a fun fact. So this is something that I found so interesting even to this day, is that the case when p equals 2, the sum of the reciprocals of the squares, 1 over n squared, crazy enough, this thing converges to pi squared over 6. Okay, and what's amazing to me is that this sum really has nothing to do with trigonometry or circles, and that's really where pi usually comes in, but pi shows up in this series. So actually Euler proved this. Forget when, 1800s maybe, but yeah. So that's really cool. And this is called the basal problem. It's figuring out the value that this series converges to. That's the basal problems. So that's something cool if you want to look it up in your free time. I find it very interesting. All righty, so that's all I have for tonight. So short class. Yeah, so that's it. So if anyone has questions, please stay behind, and I'll see you guys on Monday.